The next presentation is really a uniquely Houston story. So I'm going to set the scene a little bit for Dr. Cohen here. Is in the cardiovascular world, we're all aware of this. This is the front page of Life magazine, and it was a feud that existed between Dr. Cooley and Dr. DeBakey. Now, exactly how the story played out depends on whether you're in the DeBakey camp or the Cooley camp. It doesn't really matter. But this was all around the artificial heart and the use of the artificial heart. And it's had many, many challenges, across the years. This is to remind me to say that Billy's new name is going to be Mr. Magneto. And he first presented at Pumps and Pipes in 2007 down at University of Houston. And at that time, he had this crazy idea, now commercialized and being used in patients. If I think it's crazy, it usually means it's a great idea, in which you put a North Pole and the South Pole on catheters which sat adjacent to one another in an artery and vein and cut a hole. That's essentially how you create an arteriovenous fistula to let patients go on dialysis. So Mr. Magneto has continued his interest in magnets. This is not exactly magnets. When I looked up from pictures of you, Billy, you're going to have to explain this one. Don't quite know what the story is behind that. We think of him more, playing, in a band down in Midtown somewhere. But Billy basically took on with a very talented group of engineers, Bud Fraser, I think it also deserves a lot of credit, an Australian engineer, to take on this idea of doing something completely different in terms of creating a magnetically levitated heart. So Dr. Magneto continues, and he's very kind. This has been in a lot of press around this recently. Very kind to come and have a return to Pumps and Pipes. And Billy, come and tell us about it. And after that, we're going to invite Marvin Atkins and Eric Pede and two of my partners to come up, and we'll ask you some questions. Thanks, Billy.
Thanks, man. Well, thanks a lot for the opportunity, Alan. My wife got me a t-shirt that says, "Help, I'm talking and I can't shut up." I put way too much content in this presentation. I'm going to skip around a lot and I'll nail through it. But this is a very, very Houston-centric story. This is some of the great pioneers that Alan just talked about that worked in this space. I'm going to describe some of their work, where things have been over the last decade, and the work that we're doing now that I'm pretty sure will give us the world's first permanent artificial heart. Before I tell you what we're doing and where we're headed and what we've done recently, I want to say a little bit about the past. Every talk, though, you have to start off with a disclosure. BioVaCor is a privately funded, venture-backed company. I'm the chief medical officer and I have equity. I'll try to maintain equipoise, but I encourage you to listen with the appropriate filters in place. Everybody knows heart failure is a big deal. It'll affect a fifth of the people in this room. Over 5 or 6 million Americans have it, and 160,000 Americans, actually that's a very conservative estimate, will die of heart failure every year. This is our transplant statistics. The busiest transplant year we ever had was last year. We did 4,167 transplants in the United States. So 160,000 are going to die from heart failure conservatively. We get to transplant 1 in 40 of them. We need an artificial heart. This is not a new idea. Denton Cooley and Michael DeBakey, that used to be partners and pals, were working on an artificial heart with Domingo Leota, who you saw in the slide that Nicole showed earlier. While Dr. DeBakey was out of town in Washington, D.C., getting additional funding for the project, Denton Cooley implanted it in a patient without his permission. That went over really well. That was the beginning of that Life magazine feud. Dr. Cooley got fired, went over. He had already founded the Texas Heart Institute. He fired everybody in the lab. They went over there. They didn't speak for the next 40 years, Dr. Cooley and Michael DeBakey. This is the patient, Haskell Karp. He stayed on the device for 64 hours, but started hemolyzing, meaning the blood was breaking up. It was killing his kidneys. They did an emergency transplant way before they really understood transplant science, and he tragically died 32 hours later. So he only lived for 4 days. Still, it was a monumental first, a very brave patient, a tragic outcome. That started this big feud that just Alan talked about, and as I mentioned, For 40 years, they didn't speak, but the competition that they had, being separated by a single parking lot, some say was a big determinant in building the Texas Medical Center. Throughout the 80s, the two of them combined did more heart surgery than was done in all of Europe. I actually got to be trained with Michael DeBakey. I was his last chief resident. I then went to Boston for a while and then came back and became Denton Cooley's partner. That device that was implanted in that brave patient is enshrined in the Smithsonian Institute. You can go visit it. It was a very simple device. It had two air hoses that went through the skin, because your heart's two pumps, right? One pump takes the venous blood from your arms, legs, guts, and brain and pumps it to the lungs. The bright red blood comes back from the lungs, and the second pump pumps it out through the trillions of capillaries in your body to every cell. This had balloons in it, and as the balloons inflated and deflated with air, it would force blood out of the device, and unidirectional valves turned it into forward flow. As I mentioned, that original device is enshrined. It's not around anymore, but its descendants are. How many of you remember the Jarvik heart from the early 80s, Barney Clark? The exact same device. Improvements in manufacturing and materials. Then it was called Symbion. Then it was called CardioWest. Now it's called the SynCardia temporary total artificial heart. The FDA makes them use the word temporary because, well, you've got air hoses through your body, which is not ideal, although brilliant clinicians have learned to maintain those well. You have a box here that's going chickum, 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 chick 100 times a minute, 24 hours a day, 7 days a week, 52 weeks a year, and it wears out. That's okay. It's outside the body. You can swap it out. In fact, they do swap it out every 3 months, which is a technical shortcoming. The real tragic thing, though, is this part in your chest is also going chukka, chukka, chukka 100 times a minute, actually 120 times a minute. And when it fails, you die that minute. And so since the failure modes are capricious, you don't know when it's going to fail. The average time that one of these is in a patient is about 90 days, and it's used to keep a patient who's already approved for transplant but is deteriorating to keep them alive until you can find them a heart. Let's do the math here. If it's doing, let's say 100 times a minute, that's 144,000 heartbeats in a day. It's 52 million heartbeats in a year. No man-made device can do that. It's why we never succeeded making airplanes with flapping wings. Still, a lot of lives have been saved by this. Keep patients alive until they get a transplant. We had one patient who went 4 years, but then his device failed and he died in his sleep. There's mythology about a patient who's 7 years out in Europe. I don't know. A lot of strokes, a lot of infections. It's noisy, but it is the best technology we have and the only artificial heart ever to make it through the FDA. And there are still some centers that use it. The busiest year in the United States, they put 176 of them in. Last year, I think they put in 35. The doctors don't really like it. The patients don't thrive. There are some centers that do good work with it, but most centers have turned away. So Abiomed, a giant company that just got acquired by Johnson & Johnson, through the late 90s, they said, we can make a better artificial heart. They made one that didn't have an external drive box. It was a big, complex device. Bud Frazier, my friend, mentor, and partner, did a lot of the heavy lifting on this. In fact, at the Texas Heart Institute, they did 150 cows with this. And at Louisville, University of Louisville, they did another 150. And then in 2001 and 2002, around the United States, they implanted 14 of them. That's right when I came back from Boston to join Bud Frazier. Of those, only 4 of the patients lived longer than 9 months. The device would break. Too many moving parts. Again, 144,000 heartbeats a year. One patient went 17 months. When his device broke, they said, okay, we can take you back to the operating room and change this out. And he said, please just let me die. He'd had some strokes and some other problems. So it was big. It consumed tons of power. It was noisy. It didn't balance well. But the biggest problem was the durability. So, at that point, it didn't look like we were ever going to have an artificial heart. That said, the hubris of the French, they're working on a project now. They started in 2010. This is gone now, completely gone. In 2010, they started the CARMAT project. Very similar to the AbioCor, better engineering, better materials. It uses biological surfaces. The whole inside is lined with the heart sac of a cow, pericardium. Do they have it right? I don't know. I wish them well, but it's a big, complex device. It's hard. It wouldn't fit in most of you here. They've actually done 70 patients. In the first 40, a third of them died when their devices failed. They now have 2 patients that are out 2 years. They did an early feasibility study in the United States. They were going to do 5 patients, but after 3, they shut it down because 2 of the patients died when their devices capriciously failed at 3 months. And so they're now on hold in the United States. I wish them well, but it is a big and complex device. So that's all I got. Thank you. No, I'm just kidding. So right now it sounds like we're never going to have an artificial heart. And a lot of people thought that, so they said, we give up. Let's not make an artificial heart. Let's just make an assist pump to help a weakened heart. Leave the heart in place, let it do what it can do, and let's just give it a crutch, an assist. This was the first one. Right after that original experience with the artificial heart, Dr. DeBakey and the people here in Houston shifted focus. You'd leave the diseased heart in place, but it was a pump that would take blood out of the main pumping chamber and accelerate it into the aorta, doing some of the work. This is what it looks like. It's a big device, but it also had the same challenge. It could only last a year and a half tops. Still, it would keep you alive while you were looking for a transplant organ. And that was its main use, was to keep patients alive on the transplant list. So it didn't change how many patients you could transplant. It just changed which ones they were. Still, it did well enough that they said, let's do a destination study. We know they're all going to fail at 18 months or 2 years, but maybe that's still better than being on medicines. And they did a study, and lo and behold, more patients were alive at 2 years with this device than taking pills, even though 75% of them had died when their devices had failed. So the FDA approved it as a destination device. This taught us that big, goofy pumps can keep patients alive as an assist, but we needed better pumps. And we need a better remote. That's what our good friend Rich Wampler was thinking about. And this guy, we call him Captain Hemo, one of the most brilliant guys I've ever met. He was on a missionary trip to Egypt, and he was watching some Egyptian workers use a shut-off, a Archimedes screw, to pump water up a riverbank for irrigation. And basically, it's like a big piece of fusilli pasta, and if you turn it in a tube, water rides up like on an escalator. And Rich Wampler sat and watched him and said, wow, if you can use that to move water against gravity, maybe you could use it to move blood against pressure. And he came home and he built this crazy thing. The little impeller is at the back of that white tube, and there were no motors small enough or powerful enough to spin it as fast as it needed to go in the 1980s when he was working on this. There are now. So he was going to put the motor outside the body, strapped to the patient's leg, and have a spinning cable threaded up. It's femoral, not femoral. Threaded up the femoral artery to this tube across the aortic valve, and if he could spin that little turbine fast enough, he could pull a meaningful amount of blood out of the heart and send it along its way. Now, you couldn't go home with it. You couldn't even leave the ICU. You had this crazy thing threaded up your body, but for someone in acute crisis, maybe it would work. He went and showed that to Bud Frazier, my mentor that I showed you. And there's actually the first successful implant. It was really funny. He said, Dr. Frazier, we're going to spin this thing on this tube and put it across the aortic valve. Nobody had ever accelerated blood with a rapidly spinning anything. And Bud Frazier said, well, isn't that going to be like putting fruit in a whirring blender? And Rich Wampler said, well, Dr. Frazier, it's like running your hand through the flame of a candle. Your hand sees the flame for just an instant and then cools off. And next time, it may miss the flame. It may go out through the regular aortic valve. Or if it sees it, it will just see it for an instant. And Dr. Frazier said, oh, very good. After doing 30 or 40 cows and showing it didn't break the blood, they did this very brave patient. This patient had had a heart transplant 6 months earlier. He was in acute rejection. His heart was going to die. His lungs had filled up with fluid. He wasn't making any urine. His lips were blue. They were going to pronounce him. Dr. Frazier said, well, we can try the new pump. They take him to the OR under x-ray. They sew a graft onto his femoral artery. They thread it up around the arch across his aortic valve and turn it on. And within a minute, his lips go from blue to pink. He starts peeing gallons of urine. Over the next 12 hours, his x-ray cleared up. Interestingly, I don't know if you knew this, the cable broke at 2 days. But by then, they put him on OKT3, a new drug to reverse rejection. His heart started beating. He went home 10 days later and lived another decade. It was the first time a rapidly spinning anything had been put in a human. It was a big deal. They had a press conference. All the newspapers and journalists from Houston were there, and he was presenting the data. And someone in the back raises their hand and says, Dr. Frazier, congratulations, that's an amazing case. You know, oh, yeah, it was a bit of a shoestring catch. Couldn't have done it without Rich. And they said, what keeps the rapidly spinning turbine from breaking the blood? And he says, well, it's going 2,700 times a minute, but you see, it's like running your hand through the flame of a candle. And anyway, everyone was very congratulatory. They go home. Rich Wampler comes up to Dr. Frazier and says, Dr. Frazier, congratulations. Oh, thanks, Rich. We couldn't have done it without you. And he goes, one correction. You said it went 2,700 times a minute. You know, it's 27,000 times a minute. And Bud apparently swallowed, looked at his feet and said, I guess it's a good thing I didn't know that. I never would have tried it. Bud says that's apocryphal. Rich Wampler swears by it. Anyway, as a result of that original success, there are now tons of rapidly spinning pumps that we implant in patients to keep them alive. This is the HeartMate 2, the first commercially successful one. Several of the people that innovated the Micromed Reliant are here in the room, heroes in the space. This changed the world of managing heart failure, and that pump is now totally obsolete and has been replaced by better pumps. You can see how much smaller it is. The first one in the world successfully was implanted at the Texas Heart Institute, go Houston, in November of 2003. So much smaller than the big clunky pump I showed you before. Easier to implant, so patients survive better. It uses a lot less energy, a fraction of the energy, but it's so much more durable. There's a patient in San Diego that's had one for 21 years now, and thousands of patients that have had them for more than a decade. So that's changed the whole complexion, and now there are tons of rapidly spinning part. There's the Heart Assist 5. Well, that's when Bud had his next huge epiphany and why I came back down from Boston. I did all my medical school and general surgery and cardiac surgery at Methodist Hospital and Baylor College of Medicine. I was Michael DeBakey's last chief resident. That's what I say. He stepped down as chancellor at my graduation. I think he just was exasperated and gave up. But Bud said, look, these spinning pumps seem to work with blood. Let's make a spinning artificial heart. So Rob Jarvik had shifted his focus to rapidly spinning turbines. He gave us 2 of these. These things were $80,000 each. And we did an experiment with a cow where we cut the whole heart out and put 2 turbines in where the heart used to be. One turbine to take the venous blood and pump it to the lungs. The second turbine to take the bright red blood coming back from the lungs and pump it to the body. We didn't have a lot of confidence this was going to work. We were just kind of going through the exercise, but at the end of the operation, the surgical field was really dry, so we put those light blue things on. Those are Doppler flow probes, and closed the chest and thought, well, let's see if he wakes up. I go up to my office to take care of dictations and stuff. They call me 3 hours later and say, Dr. Cohn, come down to the lab. Our animal was standing and eating hay, and I couldn't believe it. And this animal had no pulse, no heartbeat. As you just saw from that picture, his heart had only 2 moving parts, and he actually went 21 days before standing up briskly in the stanchion and having the controller fall off and unplug. But so we were really excited by this, and we took those 2 turbines and washed them really good and did another animal with them. that one didn't go as well, and we injured the pumps taking them out. We wanted to do it again. Rob Jarvik said, guys, those pumps are really expensive. Luckily, Micromed was in town, and Bob Benkowski became our patron saint, giving us an unlimited supply of these pumps, basically, and working on some of the code and software. He's now a partner for this work that we're doing that I'll get to shortly. These pumps, though, the geometry, it wasn't well configured for just sticking in the heart like those Jarvik bullets. Luckily, we were able to come up with a way to do it. We took Dacron polyester and sewed little cones. And then I went to Medical Device Prototyping Headquarters. And I kid you not, if you're trying to make something or figure something out, just walking in the aisles of Home Depot, if that doesn't inspire you, you need to widen your blinders. And used actually drywall tape, the stuff you put on the wall to hide the seams so when you paint over it, you can't tell where one drywall panel ends and the next one begins. And bath and tile caulk, that's the stuff you put around the potty upstairs so it doesn't drip on the stove. And built these little piñatas that were Dacron on the inside and multiple layers. Yeah, I don't know why you guys have so much trouble making cuffs, Bob. I made these in my garage. Anyway, multiple layers, inside joke, sorry. Multiple layers of fiberglass mesh or whatever the mesh is made out of, and the silicone so the needle holes wouldn't bleed, they wouldn't tear. I could cut them in the OR and they wouldn't fray. And on the inside was beautiful Dacron, which the blood seems to like. And then went in the animal lab. This is a cow. He's on bypass. That's what the big hoses are. Cut out the heart. So one of these to the right atrium. There's a Micromed turbine. So a second one to the left atrium. There's a second turbine. Cross them so the left turbine goes to the aorta and the right turbine goes to the pulmonary artery. There's that animal 7 weeks later, walking on a treadmill, eating molasses off of Bud Frazier and Denton Cooley's hand. I'm standing there holding the molasses. They cropped me out for some reason. Anyway, we did this over and over and over again and thought, this seems to be the answer. Here's the AbioCor heart that the Abiomed spent $250 million developing before they gave up. That's on the right, over 120 moving parts. That's our little Micromed artificial heart on the left with only 2 moving parts. We did it with a bunch of different kinds of pumps. In fact, here's a summary of the first 68 of these we did. So a monumental amount of work. I mean, thousands and thousands of hours of brilliant people and brilliant team. And I should have said this from the get-go. What I'm presenting is the work of dozens of brilliant engineers, animal techs, scientists. It's been just a grail quest. Anyway, in all 67 of these animals, we'd cut the heart out, we'd sew the pump in. Only 30 of them went more than a week. Only 8 of them were able to walk on the treadmill. We had a lot of infections, but it looked like it was working okay. And these animals, when we'd splice and dice them and look at their brains and their liver and kidneys, they looked like they were healthy. And based on that, we did have some problems with computer control and clotting the right pump from the veins, and there were some unmet challenges. But it seemed to be a pretty good idea. It was going to be a lot smaller than any of the pulsatile devices. It was going to use a lot less power. It's going to be much more durable, shouldn't wear out ever. So Bud said, well, maybe we ought to try and put this in a patient. I couldn't have done it without his cover. He's this legacy, famous guy at built the Texas Heart Institute with Denton Cooley. And I said, yeah, I think that's a great idea. We knew, though, if we sewed drywall tape and bath and tile silicone into a patient, that would be the end of our medical careers, and I would learn a lot more about how they make license plates in the state of Texas, which didn't appeal to me. That said, there were things on the shelves and aisles of the Texas Heart Institute that were approved for implantation, albeit perhaps not in that exact configuration. Instead of drywall tape, which is $5.99 for a 50-foot roll, we use hernia mesh, which is $2,000 a sheet. Instead of Dacron polyester from the fabric store, we use cardiovascular patches, again about $1,000 for a piece about the size of a Kleenex. and then medical silicone, and put it all together into the world's first continuous flow total artificial heart, where everything in this picture is approved for implantation, albeit perhaps not in that exact arrangement, except maybe that black band tie on the aortic outflow. We did 2 cows with this exact configuration. It worked great. It was easy to put in. We didn't have to wait long for the opportunity to put it into a patient. This is a gravely ill patient with systemic amyloidosis. So we're a rogue population of cells in your bone marrows cranking out a protein. It had gone to his liver, his kidney, and heart. Very unfortunate. He was in liver failure. He was in kidney failure. He was in cardiac arrest, being kept alive by a pump at bedside. He was minimally responsive. We talked to his wife, who said, he's an engineer. He would love this. Go tell him. And yeah, I totally support it. He kind of nodded. He was on the breathing machine. And there's his x-ray hours after surgery. And here he is 2 days later, awake and working on his computer. You could see how yellow he is. That's liver failure. He's on dialysis, but he had great flow and pressure and woke up. And we looked, and he only went 5.5 weeks, but it's because we turned him off. His liver failure continued to progress. He got where the circulating toxins in his blood wouldn't allow him to be awake, and his family asked that we turn him off. And it was very, very sad. Also, he started coughing up blood, and we bronched him, put a tube down, and found that he had amyloid in his lungs. We were thinking if we could keep him alive long enough with this, he could get physical rehab, get a bone marrow transplant, and then maybe we could do a heart, liver, kidney transplant on him. But when we found the amyloid in his lungs, and because of his progressive liver failure, that was the end of his life. We got some great publications out of it. Bud and I got to go to Lincoln Center and do a TED-Med presentation. We got a lot of lay press coverage. That's the thing I made in my garage on a full page in National Geographic. The coolest thing, though, is when I was little, I've always been a science nerd. I subscribed to Popular Science. It would come to the house, and I would digest. I would read every page, every advertisement. In fact, when it was a day late, I'd pace for a day waiting for Popular Science. Being on the cover of Popular Science was a mic drop moment for me. I thought, go home, wait for a happy death. I'm done. Actually, though, the most important thing that came out of that initial experiment is we met this young man. He was young at the time. He was in his 30s. But he had spent his PhD developing a rapidly spinning artificial heart that nobody in Australia, he was from Brisbane, Australia, very few people thought had any future. They thought he was totally barking up the wrong tree. He knew who Bud Frazier was. He didn't know who I was. We didn't know of him. But now all this publications and lay press about the continuous flow, pulseless human, and he goes, God, Bud Frazier believes in this. So on his own dime, he travels to Houston. He's got a 30-minute meeting with me that day. Gets off a 16-hour flight, comes in, looks like he needs a haircut and a toothbrush. Dumps out a bunch of stuff that looks like car alternator parts on my desk. 6 hours into our 30-minute meeting, I'm realizing this guy is a time traveler. He has figured out a solution that's going to address all the challenges we had with our 67 animals. And I said, listen, where's your team? He goes, they're all over. 2 of them are in Aachen, Germany. One of them's in Brazil. One's in Brisbane with me. Another one's in Sydney. And I said, what would it take to get them all here for a year to see if we can make this thing? He'd never made a functional one. He had it all figured out. He made a thing hooked with tubes with an axle and an external motor, kind of like Rich Wampler, but that's as far as he'd gotten. And he said, if I had $2.5 million, we could come here for a year and a half. And here's our patron saint, American-made artificial heart. Buy it today, sleep on it tonight. I went and met with him, told him the whole story. I'd known him from before. He sent me to his wife, Linda, because Linda's the naysayer. Worked her. A week later, we had our check for $2.5 million. The whole team came down. This is the original team that came down. They're all still with the program. Most of these guys were still getting their PhDs. Daniel had just finished his. Now they've all got PhDs. This is in 2012. This is the device that over the next decade we developed. It didn't look like that then, but with cuffs made by Designplex in Dallas. It's a single moving part, a double-sided disc. That side, that pinwheel, is going to take the bright red blood and pump it to the body. That Stonehenge-looking assemblage of fingers takes the venous blood and pumps it to the lungs. And these three magnets here, let's see. You can sort of see this green dot. These magnets here, this one, they disappeared. These magnets make it turn. These electromagnets are adjusting thousands of times a second to keep that spinning part floating in an electromagnetic field. There's no mechanical wear. It should last forever. Because it's so much bigger, it spins slower so it wouldn't hurt the blood. And because we have blood on both sides of the rotor, you have to use so much less energy to magnetically levitate it using a principle called zero virtual power, which is something that Daniel figured out in his PhD thesis, which is just brilliant. The cool thing about this is this device existed as a digital file. You heard earlier Sassy talk about you can print rocket engines. Well, you can print artificial hearts too. This allowed us to iterate at a vicious pace. We would make 20 different rotors a day and 20 different volutes and 20 different. So this was a super iterative process because you can use computer programs. It's called CFD, Computational Flow Dynamics, to figure out kind of how things are going to work. But the proof of the pudding is in the eating. You have to actually test them. So all these are right-sided impellers. They're going to pump the venous blood to the lungs. All these are left-sided impellers. And they look sort of superficially similar, but you look, each one has a different number of fins and a different height, and some are back swept, some are forward swept, some are curved. Every one of these was tested on an automated rig where we not only tested them at different speeds against different resistance, but at different spacing, because this magnetically levitated device can sneak a little to the left or right and does that with intention to balance the left and right flow, which was one of the challenges we had. With our computers, we were always messing knobs. This rotor moves a little to the left pump gets a lot stronger than the right. It moves to the right, the left pump gets weaker than the right. It does that with greater facility than any of your mammalian hearts. These were the curves that came out of that testing rig. We had a computer analyze them, and the computer said, guys, this is your best right impeller, and this is your best left impeller. We then made a completely full printed 3D plastic heart. It's got the motors in it. It's got the magnetic levitation. Those three little dots here, and here are eddy current sensors. They're going to ping the rotor 2,000 times a second to figure out where it needs to be. This fully printed plastic pump with plastic impellers allowed us to test the device, and then in a moment of hubris, we actually sewed it into an animal. So here's an animal blissfully unaware that his heart was printed on a 3D printer. We could only go a couple days, though, 1 to 3 days, because these thin layers of plastic were hygroscopic. They would soak up water, and they would warp a little bit, and there were some parts in this device that have to be absolutely planar. But this let us figure out that we had our hemodynamics right, that we had the design right, that the thing was adaptive and was going to adjust appropriately. And then that led us to the trillion-dollar question. With our patient that I showed you that went 5.5 weeks, with the 67 animals we did, they had little bitty impellers spinning fast. We couldn't make a pulse. If we tried to speed it up and slow it down, you could see some time variance, but it wasn't a pulse. This device, we thought maybe we could. Should we? Do you need a pulse? Everybody in here have a pulse? No, anyway. Well, we should, in your capillaries, and that's where all the action takes place, nobody's got a pulse. How do we know? You can look with confocal microscopy, and the red cells move through in single file with no time variance. All of our animals did fine, and they didn't have a pulse, and they went as long as 3 months, and all their organ histology was fine. But a pulse might be good for washing out. We did have a couple patients that had the continuous flow turbines in that had really weak hearts, and they lost their pulse. And if they had a 60% carotid or a 60% leg artery stenosis, popliteal stenosis, sometimes they would thrombose beyond that. And we had some big strokes because a pulse keeps that washing out. And there's this GI bleeding. 25% of the patients that get these rapidly spinning turbines have GI bleeding. We think that's from diminished pulsatility. We're still trying to flesh that out. But it's certainly going to wash the pump out better. So we said, yeah, we probably should have a pulse. Maybe it's of some merit. Well, again, this is a digital pulse, a digital pump. All we have to do is time vary how fast it's rotating. And this is what we do. Once a second, we speed up by 600 RPM and decrease by 300 RPM, and we can make a 40 millimeter pulse that picks up on pulse oximetry, a thing that goes on your finger that measures how much oxygen is in your blood. And more importantly, it tells you what your blood pressure is when you put your arm in the machine at CVS. Here's our device pulsing away. On a stand, you can see my thumb and finger being driven apart by every heartbeat. The pulsatile cows did just like the regular cows. But look at that art line. How many of you would walk through an intensive care unit and see that art line and say, oh, I'll bet that's that magnetically levitated disc spinning fast and slow? It looks like a regular arterial line tracing. And a lot of people said, you can't do it. And I go, well, look. And they go, that's not that animal. I go, follow the line. It is. Well, then he doesn't have a bivacor. He does. So we've had a lot of problems convincing the world we're doing this. Well, just like they printed the jet engine with laser-sintered metal dust, here we're making our first durable implant. This is metal dust using that same computer file, and a laser melts the titanium dust together. The granules of the dust are 1/30th of a millimeter. After 12 hours, rising from the titanium dust is our pump, like Venus from the mist. Here we are in the operating room doing our first chronic implant. There's Rich Wampler on the left of the picture, Captain Hemo. The whole Bivacor team to the right there. There's the pump in place. And I got to give a nod to the Texas Heart team. Bud Frazier has built this incredible lab that many of you have visited or worked in with, that's Gil Costas, our veterinarian. There's Nick Graytrex and Daniel Timms, the core of Bivacor. There's Kelly, who rides with the animals when we come out of the OR, the animals in the stanchion underneath Kelly. It takes this kind of huge team to do this work, and there's very few places in the United States and in the world that can do this, and the Texas Heart is at the apex of that ability. So cow after cow after cow, and I'm sorry, I should have edited this because he walks faster and faster at the end. He's sort of jogging. This really gave us the impetus to approach the FDA and say, with some hubris, we think we know what we're doing. The FDA, we got a design freeze in the end of 2021. We did design for manufacturing, like we're going to machine these 3 pieces, we're going to weld them like this, we're going to polish this, we're going to put this here, we're going to epoxy this, we're going to weld that. In what order? The pump is made out of 7 machine pieces and then cuffs from Designplex and grafts. After doing 40 animals, we started working with the FDA. We went back and forth several times. They said, we want to see 5 animals in a row go 30 days with this device, and we want to see complete histology. Their livers, their kidneys, their brain, their lungs. We submitted all that data in early 2023. They're the 6 animals in our control. They had some challenges with some of the panics on the suture lines. We went back and forth. We went into the previous 30 and came up with some data. After a very lengthy back and forth, they gave us the permission to go ahead. As soon as we had gotten design freeze back in 2022, really, we put 8 of them on durability. They've been pumping for 2.5 years now without a failure. Not surprising. We knew they would last forever, but it's good to see. And 2 of the earlier ones, before we got to design freeze, have been pumping for 5 years without a failure. We did all the blood characterization showing it doesn't hurt blood, doesn't seem to injure von Willebrand factor. More on that as we learn. We've developed the wearables, there's Daniel holding the heart against his chest. You still have to carry this big lunchbox-like thing that'll give you about a day of walk-around time. There's a little monitor that you can hook up that programs your controller that you don't have to walk around with. You hook that up at night. And here's our ambition. Right now we're at Generation 1, that big lunchbox, but we're going to move a lot of the components into the can. The computer that does the magnetic levitation and that commutates, makes the motor, make the rotor spin, will all fit on something smaller than an iPhone, almost on an iWatch. That will go in the can. The thing outside will get smaller and smaller and smaller and be a much more usable wearable shown in the middle. But at that point, the only thing we're passing through our drive line is DC current. And at that point, we can do inductive coupling and pass it through the intact skin, just like you do when you set your iPhone on a charger. Inductive coupling was first demonstrated by Nikola Tesla in the 1893 Chicago World's Fair. It's not new. Adapting it for devices, there have been, that AbioCore had one, the big device that I showed you. Those technologies exist. It's going to be even easier because our device uses so little power. Once we get to that and don't have a drive line and show durability, which I'm confident we will, and show that it's safe and works well, our ambition is to be not a bridge to keep you alive until you get a transplant for those 4,000 lucky patients, but instead of a transplant for the 160,000 patients that die every year of heart failure. Where are we in that journey? Well, we arm wrestled with the FDA until November 17th of last year when they gave us the approval to do 5 early feasibility cases in the United States. Picking the sites, every site in the United States wanted to be part of it. We went to 9 very high-profile sites, and these are the 4 that we activated. The Texas Heart Institute here in Houston, Banner in Phoenix, which is the lead enroller for the pneumatic air-powered Syncardia heart that I described, Christ in Cincinnati, where the surgeon who did the most AbioCores works, and Duke, which is a very busy mechanical circulatory support pump hospital. And then activating these sites is a Herculean effort. It's like cleaning the Aegean stables. Everybody's got to come down and get trained. They're surgeons, they're anesthesiologists, they're cardiologists, they're critical care docs, they're nurses. You do a site visit, you put on courses there. They come down, we implant animal after animal. We go to the morgue and put it in human cadavers. All this centers contributed with their expertise and helped us morph our understanding of how we were going to do this. We finished training in June of this year, not that long ago. And I'm pleased to announce that July, August, September, October, and November, we did a pump each month, and all 5 of them are home with their families. These were patients facing death. Yeah, go for it. My wife tells me when people clap, I'm supposed to just sit there and take it and not interrupt. These were all patients that were listed for transplant. So this is a bridge to transplant study, our early feasibility study, which we're not that passionate about, but it's a necessary step to get to where we want to go. They said, all right, you take patients that are on the transplant list, that are waiting for transplant, but are dying. They're not going to make it to transplant. And if the patient and the patient's family consents and the surgeons want to do it, you cut out their diseased heart and sew in the BiVACOR device. If the patient survives the operation, if they don't have a horrible complication or devastating stroke and get healthy enough where they're walking in the hall and look like a transplant candidate, you can relist them. Now, we sort of game the system because it's biventricular support, we're replacing the whole heart, that precludes discharge. Why can't they go home with it? Because we as a company said, no, we're not going to send them home. They said, well, if they have to stay in the ICU and you're replacing the whole heart, they will be UNOS status 1, meaning once we list them, they'll be on the top of the list. That gaveth and it tooketh away. Look, we have 2 patients that only had the device for 8 days and 5 days, but we had one for 27 days and one for 15 days. When they got the device, they did so well, they were up walking a couple days later. If they had bad kidneys because they were dying, the kidneys rapidly returned to normal. If they had wet lungs, the lungs rapidly dried out. Why? Because we're flowing 12 to 14 liters a minute with left atrial pressures of 2 or 3. If you follow the rubric and run them like that, the clouds part, the sun comes out, the patients stand up, they walk, we list them, they get a heart right away. So right now, they said, do 5. After you submit 3, give us the results, and we'll weigh on the merits of it and maybe see if you can do some more in the United States. Last week, they called us and said, we can do 15 more in the United States. While we were waiting for that, it's coming, man. Oh, wait. It's happening. While we were waiting, we went to Australia and put one in Sydney at St. Vincent's in the Wild Wild West 17 days ago. He's doing fine. He has the new configured driveline. He's going to be able to go home with his pump. January 1st, we're submitting a letter describing the new driveline that we think will allow patients to go home. We've done 97,000 cycles. I think the FDA is going to give us the thumbs up. We'll start those 15 on February 1st, hopefully, and get some longer-term data. This is a chest x-ray with our device in where the heart used to be. A lot of people say, wait, I still see the heart shadow. That's all the atria, the beating chambers, and all 4 valves are gone. And to have worked this long and this hard on this project, when my team and I look at this x-ray, I get chills. I mean, it's like looking at baby photos of a grandchild. Very, very exciting. But even more exciting is to see this. Here's a patient, 8 days. He was on his deathbed. We cut his heart out. He's 6'4", and here he is walking laps. He went 27 days before he got transplanted. By the end of it, he was walking 2 miles a day effortlessly with cardiac output that's probably higher than anybody in this room's. He's a big guy. When we took his device out and did his transplant at day 27, every device, we take it while we're still in the OR. Those are the 2 cuffs that Bob and his organization made. You can see how clean it is on the inside. We put a camera in the device. This is what it looks like after 27 days. So, I mean, it looks like you could just put that pump in another patient. We have no concerns about the durability of this or how well it's going to work or how well it's going to last. This is our first patient that we did at Texas Heart Institute, here meeting with the board and some of the investors. And there he is drinking champagne. I've advised him to drink in moderation. So we've got a long way to go, but I think our early results are beyond encouraging. With this next 15, we're going to get longer and longer term data that will inform us in our discussions with the FDA about what our trial is going to look like. We're thinking it's going to be short and long being more than 2 years. So we're hoping it's not a lot of patients. There's a lot of precedent for why it's not going to be a lot because it's an unmet need. But we anticipate starting our pivotal trial at the first quarter of 2027. And if it's, I can tell you, right now, we've only done a case a month because that's all the pumps we have. That's as fast as we can make them. We're making them in Southern California. We got a lot of external vendors, and we put together a lot. Our team is 42 people. It's a small team. But with this next raise, and the raise is going very well, we're going to bring some of the manufacturing in. We're going to scale to 5 pumps a month. And during this last EFS, the number of patients people were giving us from our 4 sites and from the other 20 sites that were calling saying, hey, compassionate use, we got this patient. There are patients dying every day that this could save. And so I think the enrollment's going to go very quickly. In summary, I think continuous flow pumps are perfectly suited for the integration into the next generation artificial heart. I think Bud Frazier got it right again. We can make a pulse. They're going to be smaller. They're going to be more durable. They're going to consume less power. And I'm guessing, I won't say I'm betting my career, but I guess I am, that the Bivacor will be the first permanent practical artificial heart in the world. Now, I want to show one more slide. I talked about how Denton Cooley and Michael DeBakey had this big falling out over the first artificial heart. Dr. DeBakey had worked on it in the animal lab and was making great progress, and while he was in D.C. getting funding, Denton Cooley implanted it in a patient. Bud Frazier says Dr. Cooley did that because he wanted DeBakey to fire him because he didn't want to keep having to give half his salary to Baylor College of Medicine. Anyway, it was a horrible, horrible thing. But they're both great men. Bud Frazier and I both trained with Dr. DeBakey. So we were red ants at Texas Heart. Michael DeBakey, the black ant at the Houston Methodist. I arbitrarily made that distinction. I hope it's okay. Bud Frazier and I would go over when we were doing these 67 twin turbine animals, and we would go over at night and meet with Dr. DeBakey and show him what we were doing. And I swear to God, he said, "Well, you see, it's very satisfying seeing this type of work. I thought of this years ago." Hallmark of a good idea. Everybody takes credit for it. But we would invite him to come over to the Texas Heart Institute to watch an animal implant. And he'd never set foot in the Texas Heart Institute. One morning, we're getting ready to do an animal, and Frazier had invited him to come over the night before, and the phone rings, and it's George Noon. He says, "Billy, Dr. DeBakey's coming over in the tunnel." I go, "Whoa." So I called Bud Frazier and said, "Bud, George Noon just called. DeBakey is coming over to the lab." He goes, oh, I better call the boss. He calls Denton Cooley. We take this picture. There's Matthias Loewe, the great late Matthias Loewe. Here's me doing the work. Here's Bud getting in my way. Here's George Noon. Here's Michael DeBakey and Denton Cooley acting like they're old pals, yucking it up. They stayed there for the whole operation. Then Dr. DeBakey came over and stood up next to the OR field, and I showed him what we were doing. So not only does this technology have the potential to cure the woes of heart failure and the annual toll of heart failure deaths, but it can mend badly fractured relationships. That's all I've got. Thanks for your attention.
Well, I'm glad you don't sell used cars because I'd probably have a fleet of them. That was amazing. Okay, let me get Marvin and Eric to come on up here. We'll take 10 minutes of your lunchtime to take a few questions. And I'm sure there's questions from the floor. So anybody who wants it, there's microphones. Hold your hand up. Billy, we'd saved you a lot of trouble if you just done what Dr. Cooley did, you know. Do you have any questions you want to ask him, Marvin? So Marvin is one of the cardiovascular surgeons over at Methodist Hospital. Eric is our chief of vascular surgery, and he's actually used another device that Billy has actually invented. So we'll get to talk about that. Marvin?
Yeah, masterful lecture as always.
Thank you very much.
Great job. Thank you for everyone in your team for the amazing work that you're doing for these patients that really don't have options. Couple questions for you. So one, you kind of alluded to a little bit about the risk of GI bleeding, von Willebrand's factor, and pulsatile versus non-pulsatile flow, and that's really been one of the several Achilles heels that's plagued previous devices. Tell us a little bit more about the pulsatility and what you've seen in terms of the hemodynamics and hematologic effects of a pulsatile versus non-pulsatile pump.
Yeah, so patients that have a rapidly spinning turbine in place, if their heart is really weak, they lose their pulse. And about a quarter of them to a third of them will come into the hospital with gastrointestinal bleeding in their stomach or their intestine or their colon. And it's a big problem. They get transfused. And it's one of the things that I think has kept those rapidly spinning turbines from being used more frequently. And it was a bit of a mystery, but over the last couple decades, there's a new understanding that maybe it's related to this protein called von Willebrand factor. And von Willebrand factor is a big protein. It looks kind of like a W, okay? And when it sees shear, it opens up into a zigzag line. What's that for? Well, it turns out that the W is pretty inert, but the big zigzag line sticks to a platelet and sticks to an area of shear and makes the platelet stick to the shear. Why is that important? When you develop bleeding, a hole in an artery, and the blood is leaking through the hole, that's a lot of shear. The von Willebrand molecule, as it goes by there, goes, whoa, opens up, grabs platelets. It's how you stop bleeding. Well, all these pumps, these rapidly spinning pumps that I showed you, have very narrow gaps in them. In fact, the industry leading one, the gap is 0.5 millimeter. That's the biggest one. The HeartMate 2, it was 1/15 of that. As the blood goes through that narrow gap, it goes, was that bleeding? And opens up, and it's pumped right into the blood, platelets stick to it, and it's degraded. So when you actually have real bleeding, gastrointestinal bleeding, there's no von Willebrand factor around. It's all been consumed by the pump. So we all probably develop bleeding in our GI tract all the time, but this von Willebrand and a platelet or two stop it before we know about it. Depleting all your von Willebrand factor frustrates that, makes it so it doesn't work. Our gaps, as I mentioned, the industry leading pump right now has a gap of 500 microns, 0.5 millimeter. Our gap is 12 millimeters, 24 times bigger. We've already done assays showing we don't consume von Willebrand, and it turns out there's new evidence that arteries, when they do this, the lining, the intima, makes von Willebrand. So having a pulse, having big gaps, we're optimistic. We don't have any clinical data to support that yet, but we've done some blood studies in animals and now in humans, and that's part of our EFS study and will be part of our pivotal. Hopefully, we won't have any GI bleeding.
Do you think that's going to change some of the Impella pumps, et cetera, to make them to become pulsatile rather than continuous flow pumps?
Well, they can make it pulsatile perhaps, but the little things spinning really fast. How fast does an Impella spin? 35,000 RPM? Well, all depends what speed you set it. What are you going to go to 90 and down to 20? I mean, you just can't if it's that small. And there's nothing you can do about the small gaps. So I think it's a real challenge to do anything with an Impella, and pretty challenging to do anything with an LVAD. We can get away with it because we got so much more space because we cut the heart out and our rotor is, 8 times bigger in diameter.
Billy, can I just ask, I assume that biomaterials development has been a big part of the progress and future progress of this. I mean, to me, having artificial tubes that don't collect blood clots and that don't get infected or resistant to that, paramount, right? So all kinds of internal, external devices. Obviously, the heart, really important. If one of my devices gets infected, take it out, wait a little while, put another one in. Not so much the case with this. Have those developments already happened, that you're already big-time infection and clot resistant, or that's still in progress?
Yeah, so there are a lot of people. He's talking about implants that won't get infected, and that's like the holy grail. And every couple of years, people come up with some sort of biological coating or chemical coating or cellular coating. And I think people are making progress. We haven't leveraged any of that. Our device is all just polished titanium. The amount of blood it holds is so small and it's moving so fast, that helps us from a clotting perspective. But if our device gets infected, it's going to be a real challenge. I don't know what we would do.
What's the anticoagulation that you have these patients on?
Say it again?
What's the anticoagulation that you have these patients on?
So right now, there was a big trial called Momentum 3 that was of a LVAD, the HeartMate 3. It's now the industry leader. Abbott produces it because they bought St. Jude, and St. Jude bought Thoratec. But in the Momentum 3 trial, they put them on heparin once they stopped bleeding, and then bridged them to Coumadin with an INR of 2.5 to 3, and gave them antiplatelet, an aspirin. And now there's evidence to suggest the aspirin doesn't help, you just have more bleeding complications. But we're doing just what they did. Bud Frazier, who I've mentioned several times, is usually right. He says, Billy, you're not going to need any anticoagulation with this. Those 5 cows that we submitted to the FDA, they weren't on anything. They weren't on aspirin, Coumadin, or heparin because it's really hard to do in a cow. So it remains to be seen, but maybe we won't require anything. Or maybe for a short period until you cover your suture lines.
Okay, anyone got any questions? If not, I'll tell you the first time I met Billy, actually. He and I went to dinner in the now gone Smith & Wolanski, and he brought us some crusty bread. He made a hell of a mess on the table. It was covered in crumbs. And the waiter came up with one of those little scoops, and he started collecting the crumbs. And I'm looking at Billy, he's looking at me, and all of a sudden he's not looking at me, he's watching the scoop, because there were certain crumbs that were of a critical diameter that wouldn't go in the scoop. And so I see Billy put his hand under the table, and when the guy's scoop came in front of his hand, he banged under the table Those damn crumbs jumped straight up and into that hoop. And the waiter said, oh, thank you very much, sir. Said, that guy thinks
Simple
differently.
solutions
He's
to simple
somebody I've
problems.
got to work with. Anyway, thank you very much
Thank
indeed.
you very much.
Really appreciate you, and thank you for coming up.
Thank you very much. You're very kind.